how do you actually measure humidity? The device for this takes advantage of the relationship of temperatures with humidity. It's a psychrometer. Not a psychometer, but psychrometer. Basically, what you do, you've got two thermometers. One has a damp cloth around the ball, the other just plain thermometer. Evaporating water with your damp cloth will cool off that thermometer due to the latent heat going into producing the evaporation. The dry thermometer measures plain old ordinary air temperature. And by comparing the difference between those two, we can figure out what the humidity is. If it were 100% humidity, then the two should be the same temperature, because evaporation is happening slowly, just as much as condensation, no change. If the temperature is close, but a little less on our damp one, that would be pretty high humidity. If the damp one gets a lot cooler, then that air must be pretty dry, so there's lots of evaporation, not much condensation, and there will be a bigger difference. A special variation of this is the Sling Cyclometer, which you twirl around so that lots of air is moving past, helps it reach the adjusted temperature faster. Of course, our electronic meters have their own ways to measure the humidity. There are various other devices as well. Here's an example, a little bit of the table that you get for using your psychrometer, if you happen to have one. If the actual temperature, say, is freezing, and the damp one is 2 degrees lower, then it's 64% humidity. So you can get this type of table and figure out a humidity based on those temperature measurements from a psychrometer. Okay, what does the dew point mean for the weather? How does this affect things? Well, what's going to affect? How much evaporation do we have? How much condensation? How much water do we have available? How hot is it? What's the air temperature? How much water vapor is already in the air? These will affect how much evaporates. How much condenses? Well, how much moisture do we have in the air? What's the air temperature? For condensation, we don't need water on the surface, so it's a little simpler on the condensation question. So if we're getting condensation, we're seeing, say, dew forming on surfaces, then that air has to be saturated. We're at 100% humidity. The temperature is at the dew point. Okay, how can we reach 100% relative humidity? Well, two options. We can either add more water, so make water evaporate, or we can cool the air down. And cooler air means cooler temperatures, less evaporates, more condenses, until we reach the point of saturation. Of course, if we really want to have condensation happening, we could both cool down the air and add extra water. So when we get to the dew point temperature, we'll start to see water condensing. But water molecules zipping around as gas, they tend to just bounce off. They're not very good at sticking together under those conditions. But if there's a surface that water can stick to, then it can condense there, and then other molecules can condense onto that water, and so having a surface is much more effective than just trying to do this in clean, dry air. So condensation on surfaces, if we have a dew point, and that dew point temperature is below 0 Celsius, and the air cools down to that temperature, we will start to build ice. We'll have frost. If the dew point temperature is above the freezing point, above 0 Celsius, well, dew point, we get dew. Not too hard to guess that one. When does it happen? We're most likely to cool down to the dew point and have dew or frost forming if we have a clear, calm, cool night. Okay, why each of these? Well, clear, again, cloudy, those clouds tend to block the loss of heat as it rises from the ground. So a cloudy night tends to stay warmer. We want it colder if we're getting condensation. Calm, if the wind's blowing around, moving air, we're not getting as much air that's just sitting in one place, cooling down, getting cold. So calm rather than windy is going to be more suited for having our frost or dew. Cool, getting no surprise, colder temperatures goes along with favoring condensation. Because of these, we tend to see dew or frost forming on open areas rather than places that are sheltered, say under a tree or an awning, things like that. Again, like our cloud layer, that tends to trap the heat some, keep it from getting as cool. Likewise, dew and frost tend to form more on things that stick up rather than directly on the ground itself. Say bits of grass, leaves, on your car, things like that. These things sticking up, they're surrounded by air, they'll cool off faster than the solid ground does. This also goes along with the signs you see along the highway. Bridge ices before road. Well, actually it depends on where you are, so what you see. Back when I was in Alabama, the signs tended to say bridge may ice in winter. We moved from there to New York. We had signs saying bridge ices in winter. You get to say Tennessee, Kentucky. Up in New York, we had signs saying snowmobile crossing. This does depend on your climate, but why would a bridge ice before the road? The reason is a bridge, it's got air under it, which doesn't give a whole lot of insulation from the air temperature. So when the air drops down below freezing, air all around the bridge is below freezing, and it's easier for the bridge to cool down, while the road on the ground underneath is going to take more time, not nearly as much as water would, but still more time than air to cool down. So often the surface of a bridge will get below freezing before the general road surface, which means there might be ice on the bridge when there wasn't on the other road, and that may give you an unpleasant surprise if you drive on it expecting it to not be slippery. Also, dew and frost tend to form down in low areas before they form on slopes or on the top of a hill. And this is because as air cools, it gets denser and will tend to sink down. So as cold air sinks, it's going to end up down in the valleys. Slightly warmer air higher up. Yeah, that's reverse of the normal large-scale pattern for troposphere, but locally we get these things happening. So that colder air sinks down into the low spot. Colder, more likely to get down to the dew point and start making our dew or frost. This can happen larger scale as well. From here, next county west, Rutherford County has isothermal community college. What's that name referring to? ISO, same thermal temperature. It's kind of on the slope down from the mountains to the more general level of most of the Piedmont. And so, Cold air sinking down tends to move on past there to lower levels. So it tends to stay a little warmer, not dip quite as cold. Excuse me. So you've got an isothermal belt, the zone where the temperatures tend to stay a little more constant. That gives you a few more days in the spring after the last frost, a little bit later in the fall for the first frost. So a few more days growing season, and that will help with various crops. If you don't happen to live in the isothermal region though, but you want to try to not have frost on your crops, there are some other possible approaches. For example, some approaches to genetic modification are changing the surface of a leaf. So you've got little hairs or bumps or things where the frost tends to form on there, and then in that frost forming, you're releasing latent heat, keeping the main parts of the leaf a little bit warmer, not getting the freezing, and that can be the difference between frost ruining something and not quite if the temperature dips just down to around freezing. Okay, what about condensation up in the air? Turns out that also typically requires some sort of surface. But what surface is in the air? All the little tiny specks of things, dust, soot, things like that. Whatever this thing is in the air, we call it a condensation nucleus. And so, again, as water vapor is zipping around, if it happens to run into one of these things, it can stick to that and become liquid. And then as more water sticks there, water sticks to water pretty well. So gas molecules can stick there and build up, and we greatly grow from our starting tiny speck of something to a much larger, though still quite small compared to a person, droplet of water or ice crystal in the air.